Okay, good morning. So let me start by thanking Giovanni and all the other organizers for having me here. I have to say, a couple of my students actually were sitting, I don't know whether in this desk, but in this tutorial a couple of years ago, last year and a couple of years ago. And since then, actually, we've been using, in fact, AiiDA quite a bit. I don't think I'm going to talk much about that today, but certainly I think the fact that we start to have available a tool to do high-throughput calculation has changed a little bit the game, I think, in computational material science. So I have to say, I'm not 100% sure what I meant when I submit the title, but I guess what I want to talk to you today is try to show one example when you can close the loop. And with closing the loop, what I mean is that actually you start to design materials from the outset. You do your high-throughput hocus-pocus somehow, and then at the end, you go to the lab. And I think I really want to stress this point many, many, many times. You see a lot of stuff published where you predict all sorts of marvelous things. But if you don't go to the lab, your predictions do not exist. Okay? So you have some point to be brave. Find out somebody that trusts you. Go to the lab and try to make the things. Okay? And I think there is still quite a bit of skepticism between the community that this is actually working. However, there's plenty out there of communities that's been doing this forever. If you take the pharmaceutical one, they've been working on high-throughput method, not this one, but actually of other kind, for designing drugs since actually 30 years ago, okay, with good success. I think the fact that we get cure and their bank account seems to show that actually these things is successful, okay? So this is what I'm going to try to demonstrate today, that actually you can, in fact, design material and actually make it. So let me start with a big question. So what sort of playground are we looking at? So the question is how many inorganic material you can name. And here is a random list of them. Iron, steel, silicon, uranium, depending on what you want to do. So if you ask the question how many you can name, probably people will stop at about a few thousand, but in reality, what we know about is about 150,000. This is, depending on the databases you're looking at, you find roughly that this is a pretty much realistic number. So 150,000 materials, everything mankind has ever made and has ever measured. Now, it's a little bit misleading probably because to make this database, usually you need to have a very thorough crystallographic characterization. So if there is no crystallographic characterization, you don't make the database. So there might be materials that has been made but not crystallographically characterized. But a number of this order of magnitude is probably the real one. Now, if you think about how come, I only ask myself the question, is 150,000 a big number or a small number? Okay? How can you gauge that? And well, here actually is the rule of the game. So you have a periodic table, and that's non-negotiable. That's everything you have. And in fact, not all of it, because probably you're not going to use those, this column, for instance. You can arrange elements in the periodic table according to 14 space groups. In 3D, there are a few other in 2D, but in reality, there are very few 2D materials, so on the statistics, they don't impact very much. And then you can fill these cells in all the possible way. So this is one of my favorite examples. So this is the simple cubic structure, where you can fit the perovskite, where you have superconductor, magnet, antiferromagnet, piezoelectric, and all that. And this one here is the only one. It's the only material I know, single element material that crystallize in the simple cubic, and it's polonium. Okay? So the ones that you put in the coffee of Russian spice. So there are different applications for different material. So anyway, and this actually just gives you the variety of physics you can get simply by this simple rule. So when you think about this, maybe under 50,000 is a small number. That's actually what would be my guess. Now, how you arrange this under 50,000? Now, this has nothing to do with material. This I just blindly took from Google. But you can think about that actually the material from a very, very complex network. And what is interesting of this network is that you usually move in very, very small neighborhood. So because what you try to associate material with is property, And typically, you try to associate properties which are relatively local. So for instance, if you think about graphene, and you think about what can you find out similar to graphene, the first thing will come to mind is probably added to this stuff. And actually, the reason why you associate those is simply because they're both flat. It's not because maybe they have a very similar physical chemical property. It's simply because they're flat. Okay? Same story, if you take silicon, you will find germanium in the neighborhood. Same story, because silicon, germanium is essentially another version of silicon, just slightly more pricey, slightly more heavy, and so on. So essentially, that's the way you try to associate it. But sometimes the question is, are you really harvesting the fact that actually there is a full network? And the other important thing is, are we really sure that the best material, say magnetic material, is in the neighborhood of iron, or maybe somewhere in a completely different place with respect to this network? The other thing is important, actually, this network is completely different if you look at different properties. So if you want to associate material for mobility, you're going to have some connectivity to find material for magnetism, you're going to have another one. So the question is, can we navigate this material space, and is there anything new in this material space? So these are the two questions we try to answer. Now, as I said, this talk is going to be about magnetism. So we try to look at a particular case where we try to design a material that a class of materials that actually has a macroscopic order parameter. And the reason is because I think we want to see whether we can not just predict structure, but we can predict property which goes beyond the structures. So let me try to do the exercise again. So if I ask the question how many magnets you can make, again, you can start to throw up a list. The transition metal, this is the most famous, actually the most performing permanent magnet you can buy. It is in all the wind turbine and all these kind of things. Then you have some funny material which has very complex phase diagram, magnetite, and so on. So does anybody has a clue how many there are? So no more than 150,000. OK. More than 6. 1,000, 100, 200? Any guess?
500.
500, OK. Does anybody want to beat Nicola? 300. OK. So the answer is about 4,000. OK. Where actually I include everything. Ferromagnet, antiferromagnet, ferrimagnet, all sorts of possible phases. The only thing I left out is doping of materials. So if you have a magnet and it's doped with some dust, that doesn't count as a new one. Now, so this actually looks like a big number. However, if you think about materials that actually enter application, this number drops down to 5 or 6. So the reality is that there's a huge variety of magnets. Only very, very, very few are used. And let me try to do two things. First of all, when you see 4,000, the question is, this is big enough, so why you need few more? When I say 6 for application, then you say, well, these are not that many. Maybe you need a few more. And so let me try to explain two things. First of all, why you need new one, and actually why it's difficult to find new one. So why you need new ones? There are many, many reasons. This is one possible reason, which has nothing to do with science, if you like. It's just a geoeconomical reason. Most of the permanent magnets include the Earth. And the reason is because in a permanent magnet need to have a very large magnetic moment. And the Earth typically provide a large magnetic moment. Now, this is a map. This is a map come from the EU, actually. And it's a map of what are called the critical element. So are elements that you mine in places which are at geopolitical risk. Some of them for political instability, if you take a country in Africa, for instance. Some of them simply because of regulation. So if you take China, the mining industry is going through a very, very evolutionary phase now. And for instance, a few years ago, there was what was called the rare earth crisis. So the price of the rare earth went spectacularly high because it was an internal battle between miners and retailers of the rare earth. So the question is, you want to try to produce new magnets that actually mitigate the fact that you have to pick up the rare earth. Now, there is also the second good reason. Rare earths are expensive. So this is the periodic table where we color element by cost. Okay? So black one is very expensive. Blue one is very cheap. And you see that the rare earths are actually either black, purple, or pink, which means that are all expensive. And if you think about that, in an electrical car, you have about 200 kilos or so of magnets. Then you start to think about, well, magnets are becoming commodities. So if you want to make cheaper, then actually it's a good deal. And it's a big market. So it's going to reach 22 billion in about 3-4 years' time. Now, the second reason, which is much more scientifically, because you have new technology which are emerging for which a magnet does not exist. So for instance, this is the read head of a hard disk drive, and it's typically made of a sandwich of 2 magnets and an insulator. Now, what you can do now, you can drive this object with a current, so you can start to have a magnetization dynamics which is induced by a current. So this is something called the spin transfer torque effect. Now, if you want to do these devices, then actually you have open the space for magnetic random access memory, resonator, and all these kind of things. And now, what you use for read head is not good anymore if you want to do these dynamical applications, simply because iron is to dissipate too much, essentially. So the idea is now we have to find out some other transition metals, some other metals, in fact, magnetic metals, which has low loss. And this is actually an open task. And in fact, the fact that this technology has not been deployed yet boiled down to the fact that actually we don't have a good magnet to do the job. So that's the reason why you want to do magnet. Now, let's see this 4,000 that I mentioned. This is an histogram we put together a very long time ago with an experimental colleague of mine. And this actually is an histogram of magnet by ordering temperature, whether Curie or Nel or whatever, so regardless of a magnetic phase, in fact, a magnetic order. And what you see of this diagram, well, first of all, they decay very quickly. Okay? So this means that the vast majority of this magnet I mentioned are all here. So essentially are not magnet at room temperature, so are not super useful. And the other thing you find is if you go beyond the 500 Kelvin threshold, which is roughly where you should be for everyday application, you want to be a couple of 100 degrees above room temperature. What you see actually is that there is not that much. And the other thing actually you see is that a lot of the stuff is there, iron, magnetite, and so on, has been known since very, very, very long time. So it's something that's not been discovered very recently. And in fact, magnetite was first reported in this book, which is actually, this is a medieval, it's a 1700 print. So this is actually Historis Naturalis of Plinius the Elder. So this was written in 79 AD. And actually Plinius narrates a story of, apparently it was a legend, of a shepherd called Magnus, who finds 2 stones that attract each other. Okay? So this was the first report that I know of magnetism. So 79 AD, 2,000 years ago, we discovered 4,000 magnets. It's not a huge throughput, right? So it's 2 per year for 2,000 years. And as I mentioned, the good one has all been known since very, very long time. So the question is, the pitch, I think, is magnetism is rare, does not come every day, and actually it's bloody difficult to find a magnet which actually even survive a high temperature. Now, the other thing I want to mention is magnetism sometimes defies completely your chemical physical intuition. So, and this is one of my best examples. So if you want to make a perovskite out of this part of a periodic table, okay, you're going to have the 3D series chromite, manganite, and ferrite. Those are all antiferromagnet, and you can read your critical temperature. This is centigrade now. They're all pretty lousy magnet. The best one is strontium manganite is -10 C. Now, if you look at the 4D, it's even worse. So strontium molybdenite is actually diamagnetic, and strontium luteinite is a pretty bad ferromagnet. So my intuition would put here some other lousy magnet. However, if you make it, you find out that you have strontium technetium, which is an antiferromagnet with a TCO 500C. And the barium version is actually even higher. So this actually is completely outside your chemical physical intuition. I would never put that there. Now, this is not very useful because technetium is highly radioactive, so it's a little bit pointless to do it. But the point I want to make is you find singularity in your chemical chemical intuition. And the reason why technetium is that because the D shell is strong enough to hold the moment, and there is a huge distortion of the perovskite structure. So if you like, good enough gamma motor that will give you a very strong antiferromagnetic coupling. So this happened by chance. Now, so the question is, can we design magnet in a systematic way? So this is a project that took a lot of time in the making and was done with Stefano and Duke, who actually provide a lot of, actually the entire infrastructure, in fact. So let me try to give you first a very, very quick glimpse on how the pipeline works, which is not actually, in fact, specific of magnet. It's more or less what we do in these situations. And then actually let's try to discuss the magnet. So this is essentially how the high-throughput more or less work. So you have 3 steps. First of all, you have to calculate the material's property. And there are different ways you have to do that. But typically what you have to do, you have to calculate the property of the materials that do exist, and then come up with some criterion to construct library for something that does not exist. And of course, these criteria are becoming more and more sophisticated as time goes by. Then what you have to do, you have to put everything in a database that you can access and you can extract properties. And then this is really where the fun comes. You really have to start to screen, which essentially means you have to find criteria to start to look into the database and extract data that actually are reliable and useful and can allow you to predict something. So let me quickly go through. In a nutshell, what you do in the computer, you do DFT. We use VASP simply because, well, this is what Stefano started to do, so that's, we went along the line. But the reality, I think, what you really want, because the throughput is very high, you want a platform which is as robust as possible. That's essentially the bottom line. Then everything goes in A-flow. This is Stefano kind of a big baby. So this is manage the run and actually construct the database. And then this actually is where the projects start to differentiate because every property has a different descriptor. So then is where you start to get your physicochemical intuition in. So very quickly, let me, probably many of you know already. So let me give you a little bit of a breakdown of these various species. So first of all, so this is a big effort. So there's quite a number of groups behind it because as AiiDA, you want that actually the value is in the size of the databases eventually. Few data don't really do the job. So the idea is there is many people that agree to share the data in this platform, produce and share the data. And I suspect now the list is longer, in fact. I mean, Marco is here, is going to talk tomorrow, for instance. And the idea is we just share data, essentially. And project. So what is in this database? Well, first of all, you start to calculate everything has been made. So you take one of the crystallographic databases, in this case ICSD, and essentially you start to scan through and calculate all of them. Okay? The reality is, so this is what you find in ICSD at least maybe 2-3 years ago. This number keep evolving, of course, on I think about 100 or 200 new material make the database every year. There is a lot of redundancy because crystallographic characterization happen multiple times over the years, and the old one is put together with the new one. It doesn't superimpose. So you have some crystals that actually changes as a function of time simply because it characterizes slightly better as time goes by. And essentially what we did, we took all of those, well, we took a fraction of those, probably about 60, 70,000. I can't remember what is the real number now, simply because what is in the database are essentially all the single phase, all the binary, most of the ternary, and then it becomes more fragmented when you go to quaternary and so on, simply because at the moment nobody seems to have a huge interest in those, at least within the consortium. And everything is done with VASP, the GGA level, with full relaxation. Okay? So this is exactly what goes in the database. Now, and then you actually start to create libraries. So the idea for magnetism was, and probably this is not a very clever one, was to take a class of material, and we pick up the Oyster alloy, which is known to be a house for a lot of magnets. Now, the Oyster alloy are essentially as a ternary compound. They have this sort of cubic structures. Well, I mean, one of the structures is cubic structures, which essentially can be seen as 4 interpenetrating FCC lattices. And you're going to have 2 ions in tetrahedral coordination, the red one, and 2 ions in octahedral coordination. And you can have different phases depending on you occupy the sites. So you have what is called the regular Oyster structure, where two identical ions occupy the two tetrahedral site. You can have the alpha Oyster, where you have a vacancy instead of one of a tetrahedral site. And then you have this inverse one when you start to swap one that was previously in the tetrahedral in the octahedral. And in reality, there is a lot of stuff in between. So you have a lot of disordered phases of various kinds. You can have disorder on one sublattice, but not on the others, and so on. Okay? But those are the three basic structures. Now, and the color code map on the color code of a periodic table for what is known. So you find out that most of the red ions are picked from the kind of, if you like, the platinum group and the later transition metal. The blue one are picked from the more or less the 3D series and all the earth and so on. Now, why we pick up those? Because there are about, I would say, 250 known Oyster, magnetic or not, which I mean, sorry, in the ICSDs there are about 250. I think a rule of thumb would say there probably are about 1,000 that has been claimed. And of these, probably about between 50 and 100 are magnetic, are reported to be magnetic. So there are 100. Maybe we can find a few more. So what we did, essentially, we constructed this library of Oyster where we pick up all the elements you see color in the periodic table, and we try all the possible ternary combination. Okay? So if you do the combinatorial things, you find out that these are about 250,000. The number goes to 500,000 if you start to look a little bit at disorder and all this kind of stuff. So that's more or less what has been calculated. Now, and then very quickly, all this goes in a database. The database is a front end, which at least the first half of the front end look like this. And then when you can do search, you can do all sorts of things. And then typically you have structural and electronic results. Of course, there is also a back end that actually is much more useful if you want to do real things and start to do databasing and so on. Now, and then let me go to the last part, which is now we start to screen. Okay? So this is where the things become much more interesting and much more fun, if you like. So first of all, we have to establish descriptor. So the first descriptor, I think you would agree with me, should answer the question, I have this material, can this material exist? Okay, because a material with beautiful properties that does not exist remain a material that does not exist. Okay? So the first crudest criteria you can think about is you take the energy of your compound and you see whether it's higher or lower than the energy of the elementary phase you can break it into. Now, if the material doesn't pass this test, you are almost guaranteed that this material will not form. In the case, at least at thermodynamical equilibrium, when you start to form it, you're going to segregate the elementary phases, and then you're not going to make it. So if you look at this criteria, you start from your 250,000, and you ended up already with 35,000. So you get rid of about 90% of them. Now, of this 35,000, 6,000 are magnetic. So if this was the case, that would be fantastic, right? We know 4,000 magnets, we find in one go another 6,000. Now, it's not quite like that. The second criterion, which is a much better stability criterion, you have to start to construct the phase diagram of this object. So you have to check whether a material decomposed not just along the elementary composition, but along at least all the possible combinations, including binaries. So essentially, you have to check, for instance, whether this guy breaks down this way, or these are all stuff that exist this way, and so on. And you have to try all of them. So this means that actually you have some knowledge. You have to have some knowledge about the boundary of a phase diagram. Ideally, you really want to know also what is inside. However, what we found by more or less experience that actually the Hall convex become relatively flat when you go in the middle. So it looks like if you can stabilize the stoichiometry against the binary, you have a relatively good chance that at least you can make that stoichiometry in the ternary. Now, and then when you try all of them and you get at the end the fact that this is still lower than all the possible decomposition, you have fairly good confidence that maybe you eat something which is quite, that may be made. So this is how one of those phase diagrams look like. Now, just to stress that, of course, what you see here are only the binary which are stable. But the point is, when we construct this Hall complex phase diagram, and you convex phase. Now you want to construct it actually the full hull on the boundary. We just don't calculate the ones that we find in ICSD, but we also inspect for new prototype. So typically, to scan across this diagram, you do another maybe 3,000-4,000 new binary calculation. So this means that every time you have a ternary, it's about 3,000-4,000 new calculation. Now these are not just wasted, okay? Because this, of course, enter in the database, and maybe somebody will use it for something else, okay? But this is the price to pay. So if you think about, we have 250,000 possible ternary. You can immediately figure it out how many actually calculations you have to do to map the entire stability space. It's a huge number. Now, for the record, this one exists, in fact. And when we predict a stable, I didn't know it existed. And then I found out it was in some obscure Chinese journal, but it was made, okay? Now, this was a good guess because nickel, manganese, gallium is a famous phase memory alloy, in fact. So this, if you like, is the little brother or sister of that one. Anyway, now, so because you have a lot of complexity, what we start, now we have mapped the entire database, but what we start with was just to look at the intermetallic. And the reason was very simple, because actually we had already a very rich intermetallic binary databases. So the idea was, let's start from those, because at least we we can evaluate the stability relatively quickly without waiting for another 10 million or so of calculations. So from now on, I'm going to discuss only the magnets that you can make by taking 3D, 4D, and 5D transition method. Now there are 36,000 of them. So let's see how the number span out. Now, this is the summary, okay? 36,000 are possible. We found that only 250 or so passed this more rigorous stability criterion. Now, this is a much more brutal selection, okay? So this is, you see actually I drop a couple of zero. Now, and among those, only 22 are magnetic. So this is where the numbers start to be a little bit more harsh, I would say. Now, if you want to look what we call the delta 30 criterion with no particular reason, this actually means what are among the stable one, which one have a stability which is at least 30 milliV lower than the most favorable binary decomposition. So this means that actually are stable by a large energy distance, you find only 8. So these are the ones you can probably put your hands on and say, well, maybe these are real. So 36,000 to 8, okay? That's a pretty brutal selection. If you extrapolate to the entire database, you find out that probably there are 50 robust Oyster. Remember, about 60 or 70 are known, and probably 138 on total are magnetic. Now we know, because now we screen the entire database, that in fact we have 52 which are predicted to be magnetic and stable. So actually these are less than the one we know about it, which doesn't mean that the calculations are wrong. It means that actually a lot of those are actually metastable phases. And I think there is a good evidence that actually there is a lot of metastability in the Oyster family, which will make things significantly more complex. Now, so let me then, so if you have a magnet, as I mentioned, a magnet in itself is not very useful unless survive at relatively high temperature. So a quantity that you really need to get a grip on is the Curie temperature of a magnet. So what we did was for this 22, this is the list of it, well, it's some fraction of a list. We want to calculate TC. Now, so there's a lot of way to calculate TC from first principles. And I think I will mention another one just in a second. Here, what we tried to do was something slightly different. And the reason why we want to do that is because we want to see whether we can predict the TC by somehow correcting for this fact that some of this material are disordered in reality. Okay? So here how the calculation goes. What we did was we start to list material according to some of their physical chemical properties that has been calculated. Some of them are trivial, right? Volume, magnetic moment, enthalpy, and so on. And we check we check actually the experimentally measured Curie temperature. So we could do this for about 60 or 70. And then what we try to do, we try to train a machine learning method to predict the TC of a known existing one. And it turned out that you can do that because at least for two cases, there is actually only one single parameter that determines VTC. So you can do a decent job with machine learning, even if you have a small data set, simply because there is only one control parameter, depending on the two situations. So anyway, so in this way we calculate VTC, and then and these are the result. Okay, so this is so first of all we find only 3 types of magnet. Okay, the first one is Cobalt 2 XY. So XY are 2 other transition metal. Then we have manganese 2 XY, and then we have X2 no magnetic manganese and Y. That's it. We didn't find anything else. Okay, sorry, so no, there was one with iron, in fact, but apart from those, there's nothing else. So what I did here, so I know you can do a lot of intelligent stuff, but I usually try to do the most simple one, which is try to plot some of the quantity as a function of some other and see whether naked eye can spot something. So the way to read this plot is the following. The color code map on the material class, the full symbol are the new material, and the empty symbols are the one that has been made already. So they're the ones that do exist. And when you start to see this chart, you see a lot of scattering of data. So here, for instance, we plot the Curie temperature as a function of volume, as a function of number of valence electrons, as a function of magnetic moment, and so on. However, if you start to look a little bit more closely, you find out that there are, in fact, regularity. So for instance, if you look at Tc as a function of numbers of valence electrons, you see that all the black more or less line up on a line, right? If you look at magnetic moment as a function of volume, you see the green one are essentially constant. Same story, magnetic moment as a function of number of valence electrons. For the green one, actually, there is not a lot of spread of data. So it seems to suggest that there is something you can extract from this data just by looking at them. So then let me try to zoom in some of these diagrams. Now the first one is this class Cobalt 2 YZ. Now this is a simple one, and in fact you really don't need all this machine learning and so on. I mean, you could just read some literature and find out how the physics look like. So first of all, this is magnetic moment as a function of number of valence electron. Again, black dot are known, experimentally known Oyster, red one are the new predicted one, and you see that nicely line up on a straight line. Okay? Now this is not a super strange thing. This is simply the Slater-Pauling curve, so which is not something that happened for some material, some magnetic classes. So the Cobalt 2 type of Oyster really follows the Slater-Pauling curve, which essentially means that the magnetic moment is just proportional to the number of valence electrons until you reach the maximum moment, and then you start to drop down. And it's known for the last 50 years or so. Now, what is peculiar for this particular class, the Curie temperature also correlates with the moment, so in turn correlates with the number of valence electrons. So the Curie temperature is linearly with the number of valence electrons. Now, what about the new material predicted? Well, those red ones all come up here. They have a low electron count, so they have a low moment and pretty low ZTC. But then you have this guy here, Cobalt 2 manganese titanium, which seems to have a very high moment and very high TC. Now remember, there are very, very few which has a Curie temperature above 500. So this would be pretty spectacular if it is true. Okay? Now, and this is what I just said. So this beautifully loud, this is actually the Slater-Pauling curve. So you see that what happened is the magnetic moment goes up, reach maximum with iron, and then start to go down. Okay? And this is known for many, many years. Now, the second class I want to have a closer look is this X2 manganese Z. Now, this is actually an interesting one. So the way to think about those is essentially you have an FCC lattice of manganese ion, which are very far from each other and separated by some other non-magnetic ion. So what is interesting is that what the machine learning return you is return you quite some scattering of data. Again, empty symbol are known, full symbol with a name of the newly predicted one. And you see, but they are all bound by somehow, they have this upper bound which is set more or less here. Now if you scan in the literature, actually what the machine learning gives you is that there is a single control parameter for VTC of this class, which is the volume, or if you like, the manganese-manganese distance. Now, and again, I started to look in the literature. I found this paper from the 50 and the 60, where people call about introduced this curve which are called the Castelli-Canomata curves. That was a sort of a 1950, if you like, human machine learning, which essentially means take all you know about manganese and try to plot it. And what they find out is that indeed for manganese magnetism, the manganese-manganese distance is the crucial control parameter, and its scale essentially, the VTC scale with an empirical curve which depends a little bit on the nanometer's valence electron on the manganese-manganese distance only. And this red curve of these two versions depending on the filling, and you see that everything we predicted fall quite nicely within this curve. Now, what is the interesting point here? This curve has a maximum somewhere here for the manganese-manganese distance of the order of 3 angstrom. Now, however, because of the structure is you have only one manganese in this relatively large cell, all the Oyster clusters at the very end of the Castellitz-Canomata curve, so they're actually deemed to have a relatively low TC. And in fact, I think the highest one we found is something in the order of 600. Actually, this is I think this is a known one, in fact. So there is nothing too spectacular. The other thing is, if you look at the moment as a function of a manganese-manganese distance, this is roughly constant. You have manganese in octahedral coordination. So it's very likely, even in a metal, to go into something that is pretty close to 2+. And 2+ hold a moment of the order of 5. Okay? Now, this is a very interesting one. Just to show that this material are known. So those are 3 cases where, in fact, the Curie temperature can be changed by pressure linearly, simply because with the pressure you change the manganese-manganese distance, and then by not much, it's a couple of degrees for 10 kilobar or so, but still you can actually have that effect. Now this is the last class, and this is actually where we couldn't really fit any Curie temperature for the simple reason. So this is this manganese 2 YZ. Now what we found is that the 5 we predicted, they all crystallize in a direct Oyster structure. So with the 2 manganese in tetrahedral coordination. Now it turned out that all the other ones are known except 2 crystallize in the inverse Oyster structure, which essentially means that 1 manganese goes on octahedral coordination. So the point is, then there is nothing to run the regression against, because there is none of the material we know that actually follow the same structure, in fact. So we have no assessment of TC. However, one thing we know is that if there is a TC, probably it's going to be of a TC for an antiferromagnetic phase, because actually you have a manganese-manganese distance which is prone to antiferromagnetism. And also because we did in the past some work on some of those ones, and this is one of my favorite ones, is this manganese-free gallium. Now, this now has 3 manganese, 2 go on octahedral coordination, 1 goes in tetrahedral. And actually we spent an enormous amount of time to do both in theory and experiment, to do the magnetic characterization. And this is one of the worst you can think about it, because this is a non-fully compensated antiferromagnet, where you have the spin moment on the tetrahedral site, they point in one direction, the spin moment in the octahedral one in another direction, which is not 180 degrees, somehow misaligned, and the 2 angular moments point in another 2 direction again. So I actually have a 4 spin sublattices, each one of them pointing in a different direction. And to do this, you have to do synchrotron and neutron. You can just trust magnetometry. The last thing is, what about magnetocrystalline anisotropy? Now, this is a tricky one to calculate. It's expensive to calculate. However, as a first proxy, we said, well, maybe what we should look at is whether or not there is a distortion in the crystal structures. Now, in cubic structures, for those of you who know magnetism, in cubic structures, the angular momentum is highly quenched. So spin orbit doesn't really pick up, which essentially means that the magnetocrystalline anisotropy is actually going to be weak. So as a proxy, we said, well, let's find out whether there is a tetragonal distortion. So we break this cubic symmetry, and we see whether the moment can go up. Now, again, this was not something we did by chance, simply because we knew that among the Oysters, there are a few of them, particularly the manganese-containing, that actually distort. And in fact, so this is a list of the one unknown to distort. And in fact, it's not completely clear why they do distort. For some classes, particularly when you have an ion with a D8 configuration is the tellers that essentially give you the distortion at the tetrahedral site. But some other situation, so this happened for the rhodium and for the nickel case, but for some situation like here or here, we actually don't quite know why they do distort. But it's a fact that when they distort, the anisotropy goes up. So we look for distortion. And then you start to find an interesting fact. So when you distort, essentially, why a material wants to distort? Well, a material wants to distort because you find a high density state at the Fermi level, which is actually counted by degenerate state. So if you distort, you can leave the degeneracy, open a gap at the Fermi level, and reduce the kinetic energy of your system. However, another way to remove density state at the Fermi level is to Stoner split, okay? So give rise to magnetism. So the two things compete. And in fact, sorry, you have to see this because I spent ages to do it. So you see that actually you can have all possible situations. You can have a situation with material distort but does not Stoner split, the Stoner split but does not distort, or they do both, okay? Now, so when you run these things, what we find out is, oh yeah, and so essentially there is some sort of a competition between Stoner and Ian-Teller instability. And when you do the calculation, you find out that 2 of these 22 turn out diamagnetic. So essentially, they lose the moment by distortion. I mean, they lower the energy, but they lose the moment. 3 of them remain magnetic, and their property doesn't change very much. So we couldn't find anything particularly exciting. And the point is, all the ones that seem to distort are the ones that actually has a relatively low TC. So there is nothing that seems to have a high magnetic crystalline anisotropy and a high TC. Now, before I close to show what happened when you go to the lab, okay? So let me just give you a 2-minute glimpse on what else you can do when you start to have all this data. Now, this is very much work in progress, so I'm not want to be any more prescriptive. So essentially what we did was we tried to ask the question, okay, we're not being very successful with a stable one to find something which might be good as a permanent magnet. Can we broaden up our criterion and see whether there is anything, at least to start? So what we did actually, we set up some criterion that need to be matched to have a material that probably is a good permanent magnet. So what you need to have a relatively high magnetocrystalline anisotropy, which essentially means that the magnetization should point robustly in one direction. You have to have a large moment, ideally something exceeding 6 μV per formula unit, and at least a TC of 500 Kelvin. So the question is, can we now search? And the idea is, what we try to do, we try to search for, we forget about, for the moment, the Hall convex phase diagram. We just look at the material which has a relatively low enthalpy of formation, so we can actually get a larger pool. So the rationale of that is, let's get stuff that does not decompose, at least along the elementary decomposition, and maybe can be made in a metastable phase. That actually was the idea. So now, in this case, we did 2 things. First of all, this time we calculate TC, because now we have a much broader class. And we did something pretty crude. So we evaluate exchange from essentially by DFT, so by essentially calculating frozen magnon, which is through the magnetic force theorem. And then we plug some sort of an Heisenberg-like model in a mean field approximation for TC. Now, this, most of the time, massively overestimates the TC. Now, for some reason, for this particular class, it turned out that actually is relatively satisfactory. So this is a plot of mean field TC, again, experimental one. And you see that it doesn't correlate too badly. We have some outlier, and we know that. And there's something to do with neglecting some long-range interaction. But for this case, doesn't seem to be a too bad approximation. And this already shows something interesting. If you look at the magnetic moment as a function of the predicted TC, you find that TC and moment goes hand in hand. So when you have a large moment, typically you have large TC, low moment is low TC, which is good, because actually those 2 properties point in the same direction in terms of designing permanent magnet. Now, if you now do the magnetic crystalline anisotropy, and here what we do again is DFT plus spin orbit and the magnetic force theorem essentially is some sort of a, if you like, linear response approximation. Then the situation becomes severely more complex, Because, well, first of all, what we try to find out is how the magnetic crystalline isotopy correlate with all the other properties we calculate. And the only thing I think you can see is probably the most strong correlation is here. So when you start to distort, so the C over A ratio of your cubic structure is not 1, you see that we found some material with relatively large anisotropy. Same story, you seem to need to have a particular volume to have a relatively large magnetocrystalline anisotropy. Now, the interesting thing is this. When it's cubic, the anisotropy, so 1 is cubic, is essentially 0. As the C over A ratio increases, you get anisotropy. When it becomes too big, actually, you start to drop. In fact, also the TC drop down, so it's not actually good news anyway. Now, the bad news is this. When you plot everything together, so when you have magnetocrystalline anisotropy on this axis and TC on this other one, a permanent magnet wants to be here. Largest anisotropy, larger TC. And you see there is not that much there. And in fact, the color code is also the magnetic moment per formula unit. And you see that actually there are very few which are in this upper corner with large magnetocrystalline anisotropy, but large moment and relatively large TC. Now, there are a few of them, and a couple of them actually do exist, in fact, and have a relatively large magnetocrystalline anisotropy. But actually, it's not as simple. So I guess the take-home message here is when you start to do designing, and you start to actually do design among, and you want to design against a lot of properties, then actually when things start to be very, very tricky, simply because there are not that many materials that has all this property. So and the question is, can intuition bring us there, or you need to do the calculation? And sometime, I believe, actually, you probably need to do the calculation. Now, the last thing about these things is, magnetocrystalline isotopy is very expensive to calculate. So if I want to do it for the large data set, it's actually going to be an intensive calculation to do. And most of the time, you have to go all electron. You can rely on pseudopotential and so on. So actually, it's not a pleasant thing to do. So can we actually maybe save a little bit of computational resources? So what we did was nothing as fancy as yesterday, but we tried to do some little machine learning selection. Essentially, we tried to write down some descriptor, some vector of features, which include essentially what the chemical composition, the multiplicity of the ion, the magnetic moment, and so on. And we try to actually to machine learn the magnetocrystalline anisotropy. Now, what we find, in fact, actually, what we decided to do was not try to forecast the magnetocrystalline anisotropy, but just have a clue whether this was large or small. Okay? Now, why actually this is important? Because, well, if it is small, you don't calculate. Okay? If it is large, you give it a go. Now, what we find out actually is quite interesting. We found out that the best strategy was not to try to predict the ones that are hard, but to try to predict the ones that are soft. And actually, and this is, and I just give you in a second the reason. Now, what we find out is that if you look at this curve, which essentially is the rate of, so this curve actually a different machine learning method. I have to admit I don't remember actually what exact algorithm we use here. But essentially, depending on the parameter, you can either improve the false positive rate, which essentially means how many times you predict something which is not the one you predict, and against the positive rate. So ideally, you want to be here. So everything you predict is correct, and there is no misprediction. However, what you find out is that for some situation, we can predict 100%, so we don't have any calculations. So we don't predict anything soft, which is hard, but we don't predict all of them. And we thought actually this is a good strategy, because then what we do, we predict the soft one with 100% confidence. We know that what is left is a combination of hard plus soft, but what we don't miss any of the hard one. And this is important because if we would have done the other way, we would have predicted the hard one with 100% confidence, but left out some of them, because we can predict only 60% of those. So this means that actually we would lose a third or so of the good one. And because they're so rare, this is what you don't want to do. Okay? So that was the idea. And then just to give you a feeling, and you say, well, it's 30% is not a big deal. Now, if we start from 230 candidates, this is what we did. 80, you calculate the magnetocrystalline isotope the hard way. You do your machine learning, you know that there are 149 remaining, and you have a 60% or so confidence. So let's say you don't calculate 30% of that, you save a 50 calculation. And if the calculations are heavy, well, that's not an indecent save. The point is, it gets better as you train. So if you have 2,000 candidates, you spare 650 of them. And if you have a $250,000, you spare 80,000. And now for heavy calculation, this is not an indecent save. Okay? So every time you have to afford a large scale set of calculation at a deep level of theory, if you have a chance, I think it's a good idea to try to gauge a little bit what is very important to calculate, what is probably less important to calculate, because you might save yourself some time. Okay, finally, so I said that eventually I really want to go back to the lab. So actually, we went back to the lab. So this is one of my favorite pictures. So you see, this is me. Okay, so I'm in the lab. As you can see, I'm just observing people doing things. And of course, you don't go in the lab with your jacket. So this was more like for newspaper. But anyway, but actually, that's the way you make it. So this is arc melt. So essentially, what you have is you prepare your metals and you heat them up with a very, very intense electrical current, essentially. And essentially, we try to make 4 of them. So we try to make 2 of the one we predict very robust, and 2 of the remaining manganese 2 base, because we want to see whether there was some exotic magnetism. Now, this is the first one, which I'm super proud of. So this is Cobalt 2 manganese titanium that actually was made. It came up essentially as predicted. So it's a beautiful standard Oyster phase. The lattice parameter is more or less the GGA one within a couple of percent, as more or less any other GGA calculation. We know this is disorder, so actually the site occupation is not great. And what we know is also that this is the magnetization curve. So as you can see, the magnetization curve at 4 Kelvin and 300 Kelvin is more or less the same, meaning that the magnetism is robust. You don't see hysteresis because the magnetocrystalline isotope is very weak. So actually, this is, if you like, is a magnet which is a high TC magnet, but no anisotropy, unfortunately. So it might be good for maybe some spintronic applications, certainly not as a permanent magnet. Now, interesting enough, if you look at the magnetization versus temperature curve, actually we could measure up to 800, but then you extrapolate, you come up with a measure TC of 940. By luck, we predict 938. So we know the regression has a 50-degree or so uncertainty, so that's certainly within the 50-degree. So now, of course, I'm very proud because it seems to work. So you really do something in your computer. It's actually not that simple, but then you get the material, you go to the lab, and you make it. Okay? And I'm not lying. The procedure was really, we didn't make it first, and then we reverse engineered all the rest. So we really did the right way. Now, the second one is something that also was made. This is the second robust one. This manganese 2 palladium platinum. Now, it turned out, unfortunately, this actually crystallized in distorted structures. In fact, we couldn't, funny enough, actually, GGA predicted still the cubic one because if GGA was done at the ferromagnetic cell. So actually, if you repeat the calculation in the antiferromagnetic configuration, in fact, you get the distortion. So this is an antiferromagnet with, actually, we can find out in the susceptibility at least 2 TC, so 2 Nel temperature of some kind, all between a very low moment situation. So these are 2 antiferromagnetic to antiferromagnetic transition of some kind, both of them very low moment. And in fact, when we did the, when we calculate the exchange, and then we did some Monte Carlo for measuring the susceptibility, we also find the 2 transition, again, at low moment transition, at around the TC where the experimentalists saw them. So what we believe is that this is just a complex antiferromagnet, not with a very spectacular TC, maybe 500 Kelvin or so, but actually, I think, prove the point that actually can be made. However, when the magnetic structure becomes significantly more complex, then, of course, in principle, you can still predict it, but then you would need to run another big set of calculations where you start to look at different magnetic cells. OK, so let me conclude here. So I guess my point here is that what we did is the exercise is really the one to try to find a needle in a high stack. So you have a huge material space. You know that magnetism is rare, so actually it appears only very few times. So, and I think actually, if you want to do systematically, you really have to start to think about this kind of very large-scale integrated way to do it. I think now that we know best, I think next time we will probably be quicker because our prototype will be constructed in a much more clever way that eliminates a little bit of waste. But still, I don't think there is any way to sugarcoat it. So it is still about doing a large-scale calculation. Sometime you find the needle, but the needle really needs to speak to you. So finally, so these are the people who did the job. So these are the guy in my group, and these are the guy in Stefano's group, and some of those pay. Thank you.